So now that we have a distance, how do we actually control them and tell them where to go or how to keep their position? We're going to talk about distributed state estimation and the difference between that and a centralized estimator and the strengths and weaknesses of each one of those approaches. We're going to talk about the future work in the next summer and the next year, and then finally open up the floor for any questions that you may have. So first, talking about CubeSats. So a normal satellite is going to be about the size of a car. The Hubble Space Telescope communication satellite costs tens of millions of dollars to manufacture and then hundreds of $millions to launch into space because rockets are very expensive. Where the benefit of having a smaller satellite like a CubeSat, where the satellite's only basically a 10 centimeter cube with a mass of no more than 1 1/3 kilograms, is that they're just a lot cheaper to manufacture. And if you wanted to do, as a small research group, just launch a satellite to perform a small test, it would be a lot cheaper to run that. And these can be launched a lot easier because you can actually send them up to the International Space Station, and then the astronauts can just launch them from there, which is a good solution. It's still a little bit expensive because the astronauts' time is very valuable, and they only have so much time on the International Space Station. So another good solution is to use them as a secondary payload on another launch vehicle. So if you find a rocket that's going to the right destination, maybe you could put your CubeSat on there for just a couple $1,000s to launch it into space instead of having to set up your own launch, which is a great solution and is helping CubeSats rise in popularity. So basically ever since 2013, CubeSats have been becoming more and more popular. To date, over 1,300 have been launched, about 200 each year. And then in the next coming years, we're looking at 400 to 500 scheduled to be launched, with a pretty high success rate of these CubeSat launches as well. And there's a lot of different fields in CubeSats, everything from having solar panels, whether you have them just on the sides or you actually have them fanned out in an origami approach, what kind of batteries you have, what kind of processor you're running. But this presentation is mostly going to focus on the guidance, navigation, and control. So how can we figure out where these CubeSats are, and how do we tell them where we want them to go? So formation flying and CubeSats are a benefit over a single satellite, because if you just have one large communication satellite, let's say, you're going to have solar panels, a battery, a communication antenna to talk with Earth. You're going to have a couple different sensors looking at the atmosphere, maybe a couple different cameras. And if any one of those sensors fails or has some problem, then you're either stuck with just not having that sensor, or then you've got to basically launch a whole new satellite to replace it, which isn't a great solution. So if you split all of the different parts of that satellite off and had them all be an individual microsatellite, then if any one of those components failed, you could just replace that one part of it, and it would be a lot easier and cheaper. These can also be better because you can take multiple measurements of the same data to try to get a better average of the sample. And then, so if you're going to have formation of CubeSats, or if they're going to be anywhere close to each other and you want them to keep their position, you need some kind of relative position measurement. So whether that's LiDAR, which will just give you a distance to your target. There's star trackers and sun sensors, which are a lot more common for just satellite positioning when you're not orbiting Earth. But if you're around Earth and you're relatively low orbit, then you can use GPS, which is a great solution. It gives you about 1.5 meter accuracy. So if you're anywhere, 100 meters away, 1,000 meters away, all the way on the other side of the Earth, that's a great solution because it's really easy. You just put a GPS antenna on there. But if you're going to have satellites that are operating close to each other, if you're trying to dock them or have them in a really tight formation, then a 1.5 meter position inaccuracy is going to be a bit much for that. So what NASA's been trying and what we've been testing is using vision-based pose estimation. Some scientists at NASA created the smartphone vision guidance sensor, which is basically just an Android smartphone with a pretty low-cost processor and camera. And then they have what's called a 3U CubeSat, where it's basically 3 of the 10 centimeter cubes stacked on top of each other. And then they have a couple LEDs on there so that looking at that satellite, you can get a good pose estimate. So you can know its distance away and its orientation. And that works quite well. One of the things that's a little bit difficult with this method is identifying different CubeSats from one another, because there's only so many orientations of LEDs that you can put together. Whereas the method that we propose is using AR or augmented reality tags, where each CubeSat would have one of these tags on each one of its faces. And these tags are basically a black square with then a bunch of black and white square pixels inside of them. And knowing the size of the black square allows you to determine the distance and the pose, and then the individual changing the pixels on the inside allows you to change the ID of the tag. So we can have each CubeSat have one of these tags on each face and be able to identify its rotation fully, as well as being able to identify 10 or 20 different CubeSats very easily from one another. And we've done a little bit of testing on this. So this testing was just done using a Raspberry Pi camera, and then the processing was done on a Raspberry Pi. So then we tested 3 different resolutions: 640 by 480, 960 by 720, and 1280 by 960. Higher resolution just has more pixels, so it's going to be more accurate, but then you're also going to need more processing power to get the same frame rate from the camera. We tested this up to 3.5 meters. We can see the low resolution cameras are getting relatively inaccurate at -10 centimeters. But then if we cut that distance down to just 0 to 1 meter, we can see the error is quite linear for all of these different cameras. So we can just subtract off that linear offset, which might be just imperfect calibration or the tag size not being 100% perfect. Then we can get the error down in 1 meter distance down to about ½ centimeter, which is really accurate. And then we also did some testing that was just single degree of freedom. So just the tag is perpendicular and then moving it back and forth, which is a pretty easy example. But we also did some testing here where we have 3-dimensional translation and a little bit of orientation as well. So we had 2 laptops here. Each of them has a camera, and then we have a stationary tag. And then we measure the pose of the whole system with each of the cameras, measuring the other 2 tags. And then we compute the distances for each leg of the triangle with those, and then we average both of the camera's measurements. So in the bottom left, there's a MATLAB plot of just the estimation of what it thinks the triangle looks like. And then we also computed the distance legs of each triangle and compared them to the measured values. And we got a little bit more error than was in the previous setup, an error of about ±10 centimeters, which is a little bit high, but maybe a little bit better calibration. And we've been wanting to test this in a motion capture volume as well to get really accurate different estimations of how good the position and orientation are. But so now that we have a method of determining our relative pose and position, now we can move into the dynamics and control. So basically this is a linearized dynamic model of orbital dynamics proposed by Hideg in his 2012 paper. The state vector for this is just XYZ position and then XYZ velocity. And there's 2 parameters here. It's linearized about a circular orbit and about any body. So mu is the standard gravitational parameter. We've been using the value for Earth here. And then r is the distance between the center of each mass. So we've been simulating these CubeSats in a 100-kilometer orbit, which means they're 100 kilometers above the average equator, so 6,500 kilometers above the center of the Earth. So that's the model for each one of the CubeSats. And then if we want to combine it to create a swarm of, or a formation of 3 different CubeSats, the CubeSats themselves don't affect the others. There's no, in space, there's no force between them. And so the only way they would affect one another is if they were thrusting directly at each other and pushing themselves away. But that's unlikely. So we're just kind of ignoring that. And so then we can just use a block identity matrix to stack our A and B matrices together, as well as our state vector. And then so now we have a dynamic model for all 3 of our CubeSats in the formation. And then what we did just as a simple controller to validate the dynamics is we developed a PD controller. We didn't use a PID controller because the integral term is just for steady state error, and we didn't, the steady state error it's okay right now. We didn't really need to kill it all the way to 0. And also the integral term adds a lot of oscillation and wastes a lot of fuel if it's not tuned perfectly as well. So we just didn't think it was really necessary. The PD controller was tuned, and the KP value of -1/1,000,000th, and a KD value of -1,000th. And then we developed this BK matrix, which is just our K times the B matrix, and then using our state equation of AX plus BK times X minus G, where X is the current state of the formation, and then G is the goal of the relative positions that we want them to be. Then we can control and tell each CubeSat how to stay in formation. So to validate the linear model versus, we computed the nonlinear model of orbital dynamics and plotted them against each other. The plot on the left, so the first equatorial plot is the pink and red, and then we've also got two other plots with different inclination angles. And those, at least for small angles, agree with the nonlinear orbital dynamics. And then the plot on the right is just what the orbit looks like from viewing Earth, which is the blue sort of shaded in sphere. That's around the equator. And then in the next couple plots, there's going to be these 5 points, the circle, plus, diamond, square, and star. And those are 1 point every 10,000 seconds, just to give a sort of an indication of time as it passes. So the circle is at 0 seconds, the start of the simulation. The plus is at 10,000, diamond is at 20,000, and so on. So in this plot, we've started CubeSat 1, which is the blue X at in an orbit of 100 kilometers. And then we have started satellite 2 with an offset of plus 100 meters in X. We've started satellite 3 with an offset of minus 100 meters in X and plus 100 meters in Z, so that they are about 100 meters away. And then on the right, the uncontrolled system, the satellites just oscillate about satellite 1, and there's nothing controlling them to change the relative positions over time. But then for the control system, we've defined a goal in the table of X being -10 and Y being plus or minus 10. So they're trailing behind it in the orbit. And then we can see that the controller exponentially decays the position values down to their goal. And then these plots are sort of the same as the previous ones, except instead of being 3-dimensional, they are 1-dimensional. And we've just plotted each one of the X, Y, and Z values there. So the uncontrolled system just oscillates and just continues over time, whereas the controlled system, the states decay down to the goal of plus or minus 10 pretty rapidly. And you may be wondering, so these the PD values were tuned to try to stabilize the system in one full orbit of about 90 minutes, as well as trying to keep the maximum thrust of the system as low as possible. So that thrust, the maximum thrust that this experiment resulted in was 100 micronewtons, which is easily attainable by ion thrusters or other highly efficient thrusters that would probably be the only things that are really reasonable to put on a CubeSat of this size. And so we can see the maximum thrust is about 100 micronewtons. And then over the course of 30 seconds, that decays down to 0 and then goes negative, because in space, there's no friction or anything. So if you accelerate towards your goal, then you have to start decelerating to get there eventually. Otherwise, you'll just shoot past it. But so now that we can control the CubeSats, we can talk about distributed state estimation, which is the research that we've been working on most recently, as compared to a centralized state estimator. So centralized state estimator will have each agent send all of its state measurements to the central agent. That will compute the state of the whole swarm and then send that estimation out to each agent, which works great if all of the agents don't have any obstacles between them and there's no link failure, so all of the agents can measure, can at least communicate with the central agent and take a couple measurements, then that works great. But if there's some obstacles in the way, or if your antennas aren't perfect and sometimes you have a link failure, then that won't work quite so well. So one solution is a distributed state estimator, where each agent takes its own measurements as well as the measurements of its neighbors that it can talk to, and then tries to produce its own estimate of the swarm and the formation. And that's a lot more robust to link failure. And one of the other benefits, I guess, is that it's not ever going to be worse in terms of accuracy than the centralized estimator. So if you compare these two and you have a perfect you have no link failure, there's no obstacles in the way, and each agent can measure each other agent that it can see. They will produce the same output. The one downside of a distributed state estimator is that each agent now has to compute a couple of consensus steps and run a lot of computations, whereas in the centralized, it's only the single agent. So each agent has to have a lot more processing power, but otherwise it should be very similar. We're using the method proposed by Amir Tamjidi in his paper. And so for this, we did a simple test, basically the simplest system, where it's just two single state agents with identity dynamics and control matrices. And so basically this is analogous to just a ball rolling along a ruler or something. So we've just got a single state changing, and then we've got agent 1 moving at 2 meters per second and agent 2 moving at 1 meter per second. Just sort of change their states. And there is ADA, there is some input error just to add randomness to the simulation so that we can see the difference between the centralized and the distributed estimators. So in this slide, we've ran both a centralized and a distributed estimator with this simulation. So there's in the regions in red on the time steps are where there's a link failure. So the first time step, the agents can communicate with each other, but then time steps 2, 3, 6, and 7, the systems are disconnected. So we can see that the centralized and distributed estimators at time steps 1, 2, and 3 produce identical results because they have the same information. But then on time step 4, when they reconnect again, the distributed estimator talks between the agents and tries to remove some of that, that measurement error, and it can produce a better estimate with a lower absolute error in meters for the whole system. And then that continues throughout the rest of the test as well. And then here, just sort of in as an aside, we can see a little bit into what the distributed state estimator is doing. So if we look just at the blue and yellow plots at the bottom of the graph or lower down, so at the start, we see each agent, agent 1 is blue, agent 2 is yellow, makes an estimate of agent 1's position. And then they're different because there's some error there. But then over the 10 consensus steps that we're running here, they converge to the same estimate. Then in the 2 next time steps where they cannot communicate, they are different. But then finally, when they come together again, they are able to merge and come to the same position estimate. So then talking about future work. So what we were trying to do is do a lot more work on the vision-wave pose estimation. But then with the coronavirus and everything, we weren't able to get into the motion capture lab anymore. So our goals for that are to do a lot more testing in a motion capture volume to get really accurate position and orientation estimates and figure out really how accurate the system is. As well as all the testing we've been doing so far has been static, where we just have a single tag and a camera that are just static making a measurement. But we would like to try this, putting these on ground robots that are driving around, or even putting this on a quadcopter and trying to have it follow around basically a tag on a stick and see if that works and how accurate the method is. Then another thing is to work on more of the distributed state estimation. So trying this with more complicated dynamics models, as well as doing a lot more in-depth testing with varying link failure probabilities and seeing just how resilient that is. And then finally, we're going to address some of the review comments. One of them was to compare this to the closely Wiltshire equations and other well-known models. So we've compared the linearized model to a nonlinear orbital dynamics model, but I think it would be a good idea to just compare and contrast this with the other linearized models. And then another suggestion was to test different orbit radii. So currently we've just been testing a 100-kilometer orbit, which is about the altitude of the ISS. But granted, that is a pretty low orbit, and a small CubeSat like this would pretty quickly fall out of the sky in a matter of months or maybe even a year, which wouldn't be very efficient. So maybe testing at larger radii would prove beneficial for that. And then I would like to thank Dr. Ed Duke at the South Dakota NASA EPSCoR Foundation, as well as my advisors, Dr. Hadi Fakramandi and Dr. Randy Huber. And then I would like to open up the floor for any questions that you may have.
Thank you, Alex, for the great presentation. And while folks are thinking about the questions, I have one. When you move the pose estimation model to the orbital setting, what are the specifics of images there that you would have to deal with? I mean, are there challenges? I just can imagine maybe a glare from the sun, or what is unique about that environment and doing computer vision in that environment once you move there?
Yeah, so that one of the big struggles is that there's no atmosphere to scatter light. So yeah, you would have really strong glare if your camera's pointed at the sun, but then if you're pointed at an object that's not directly lit by the sun, there's no light. So we've been looking at displaying these on a small, almost a phone screen display, so that if you're not in the light, you still have an estimate. I don't think there's really a good solution to having a measurement that's taken with the camera aiming directly into the sun. But I think that's one of the ways where the distributed state estimation shines, where you can still get a reasonable state estimate of the whole formation without having every agent measure every other.
Gotcha. Any other questions?
You mentioned that you expect the distributed consensus algorithm to have no drawback with respect to the centralized one.
In terms of just raw accuracy, there should be no drawback.
Terms of accuracy. The issue is there's no reason why a centralized decision maker cannot do the same computation that the distributed one can do. While a distributed one may be able to do the same as a centralized one for certain kinds of computations. So I think the claim is very strong. So probably you would need to check better if this is as generalizable as that. Probably for certain kind of measurements, that's true. But to prove it for the any possible measurement, I think that's challenging. And there's always the issue that consensus algorithms are typically much more time taking than centralized gathering of information and computation. And because of that, you have the additional issue of time. With a distributed consensus, you would be able to much more rarely or less frequently get updates rather than with a centralized one. And if that's the case, then since you are going to have more rare samples of the actual positioning, then any estimate that's based on time progress would have less data. So you expect, again, the centralized one to be able to end up with more accurate estimations, I would expect. So what do you think about that?
Yeah, that's a very good point. And also, even if you only had a sensor that could take measurements every second or every other interval, you could still just have less computation on a centralized estimator. I completely agree. Yeah, the computation time so far, it hasn't been an issue, but it'll definitely be something to watch out for. Yeah.
I have another question. Alex, I wonder if you can provide an insight how the satellites that you describe and the definition of swarm that you have in your work, how does it compare to SpaceX's Starlink satellites? If you have an insight about that, in terms of like a size and maybe how they define what they treat as a swarm, if there is a swarm problem there.
Yeah, so Starlink is going to be a really distributed swarm. So instead of having a bunch of satellites close together trying to do something, they're going to distribute them over the whole globe, which is kind of one of the things that you could try to do here. But this method is more for like having a bunch of satellites together So if you wanted to have a bunch of satellites that are sort of sharing instruments with each other, where one satellite has a camera and then one satellite has the communications array, where you might want them to stay very close together to try to work as sort of a single satellite, as opposed to Starlink, where it's trying to sort of cover the whole globe separately. It'll be a little bit different.
Any other questions? If there are no questions, Alex, thank you so much for the